Hi everyone, welcome back. So in this particular video, again, we're going to look at another example of retrosynthesis. And in this particular example, what I've done is I've chosen an example where we keep the number of carbon atoms the same, because that's the first thing that you have to worry about. Is there a change in the carbon skeleton? And what you will notice is both the starting material and the target, they have 5 carbon atoms. But there is a change in functional group, right? Because my starting material is an alkane. There is no functional group actually here. Whereas my product has a triple bond in it. So it's an alkyne. And the alkyne seems like, so this is an alkyne. And this is an alkane. Okay. Now the alkyne or the triple bond is between carbons 4 and 5. So you have to think about, okay, how do I install a triple bond? And this is not the case where we are adding more carbons, because if we were adding more carbons, we could just bring in the triple bond as an acetylide and do an SN2 with an alkyl halide, but that's not the case here. We have to somehow convert the single bond between 4 and 5 into a triple bond. So how do we do that? How do we synthesize an alkyne is the question. What would be a suitable precursor for an alkyne? And at this point, right, it might be hard because there are various ways of synthesizing alkynes, but we'll just start off with one and we can explore, what's the possibility. Okay, so one possibility is that we can synthesize this alkyne through an elimination reaction on an alkyl dihalide. Okay, alkyl dihalides can be converted into alkynes. Sorry, that's too small. Okay, let's fix this. Alkyl dihalides can be converted into an alkyne through an elimination reaction. The only complication is you can actually think about 2 alkyl dihalides that would give you that product. Okay, it could be a vicinal dihalide or it could be a geminal dihalide. That means we could have this molecule, which is a vicinal dihalide. 2, 3, 4, and 5, or could have this molecule, which is a geminal dihalide. So we could have vicinal or geminal dihalides. So which one is the right one? And the answer is we don't know. And so we have to think about, okay, how do we make these now? Okay, how do you make a geminal dihalide? How do you make a vicinal dihalide? A geminal dihalide is actually synthesized from alkynes. Okay, so that means you need an alkyne as a precursor to this molecule. If I have an alkyne and if I add 2 HBr into it, it will give me that geminal dihalide. But that's the same alkyne that we're trying to make from it, right? Now, even if we think about the other geminal dihalide, which would be the 2 halogens on the less substituted carbon, we would still need this alkyne as a starting material. So that doesn't seem right because we're trying to make that alkyne from this geminal dihalide, and to make this geminal dihalide, we actually need an alkyne, that same alkyne as a starting material. So that doesn't seem like the right path. What about the vicinal dihalide? Vicinal dihalides are synthesized from alkenes. Okay, so let me write down the conditions here. So for doing this elimination, either way, it doesn't matter which way we do it. So we will do 1 sodium amide in excess. And then second, you're going to quench this reaction with water, okay? Because when we do it on this vicinal dihalide, or whether it's the geminal dihalide, the reaction is going to the same. You'll make a acetylate, so we have to protonate it. Okay, so for the vicinal dihalide, the starting material is actually, okay, and I see that there's some numbering missing here, so 4, 5. So the vicinal dihalide, this guy here, the starting material is an alkene. A vicinal dihalide can be made from an alkene, because the halogenation of an alkene installs two halogens on adjacent carbon atoms. So we'll get an alkene that way. So this alkene would give us that vicinal dihalide. And now if we look at our starting material, okay, that's an alkane, this is an alkene. How do we get close to it? And at some point, like I said, it is also useful to start thinking in the forward direction, because that helps, that gives you some direction. Okay, now an alkane, as I mentioned, one synthetically useful reaction of alkanes that we've learned is the free radical halogenation. So if I do a free radical halogenation on this alkane, that is going to give me an alkyl halide as the product. But the halogen is going to end up on the most substituted carbon, okay, on carbon number 3. That's where the halogen would go. It won't go to carbon 4 or 5 so that we can make the alkene, okay? So it will go to 3. So that means we have to somehow move it over, okay? And we want to move this alkyl halide towards, the double bond. We want a double bond to form between carbons 4 and 5 here. Okay, now to make the alkene that we have here, one possible starting material, okay, is to have the halogen here on 4. Because if we have this alkyl halide, we can do an elimination using a bulky base, so potassium butoxide, to give us that alkene, which is the less substituted alkene. Okay, and now if you look, we need to move this halogen from carbon number 3 to carbon number 4. When it's on carbon number 3, it is the more substituted alkyl halide. When it's on carbon number 4, it is the less substituted alkyl halide. That's how these are related. And so the intermediate in between is an alkene, where the double bond is between carbons 3 and 4. 1, 2, 3, 4, and 5. Okay, because if we have this alkene, from here we can do an anti-Markov-Nikov hydrogenation to give that less substituted alkyl halide. And from this alkyl halide, we can do an E2 reaction. And in this particular case, we're making the more substituted alkene product that's possible here. So we can use a strong base for doing this. So we have sodium methoxide with methanol. So we start from the alkene, do a free radical halogenation, gives us an alkyl halide. Okay, this is the major product that you're going to make here. Almost 99% of the product that you get is going to be this alkyl halide, the tertiary one. From there, we did an E2 to make an alkene, which is the more substituted alkene, because again, realize that from this alkyl halide, the double bond in the alkene product can form between 3 and 4, or it could form between 3 and 1 or 3 and 2. And if it's formed between 1 and 3 or 2 and 3, that would be the less substituted alkene. So that's why we chose a strong base, but not bulky, because we want the Zaitsev product to form here. Okay, and from there we did an anti-Markov-Nikov hydrohalogenation to get the less alkyl halide. less substituted alkyl halide, and then we got the Hoffman product here. We got the Hoffman elimination, halogenation of the alkene gives us the vicinal dihalide, and then elimination on that gives us the alkyne product. So that's another example where you're doing a bunch of functional group transformations. We went from an alkene to an alkyne, through the intermediacy of several ones. And we ruled out one of the approaches. So sometimes you just have to explore all options and rule out some based on maybe some stumbling block that you get. Like maybe you get to a point where you cannot do anything further and you just leave that approach. So I hope that helps. Okay. Bye, everyone.